All right, this is AP, AB, and BC Calculus. We are doing Unit 4, Section 7, which is using L'Hopital's rule for determining limits of indeterminate forms. All right, so basically what we're going to be doing here largely is 0 over 0 and infinity over infinity. So one of the things to point out that's noted here in the exclusion statement is that there are a lot of other forms that are not 0 over 0 or infinity over infinity. We're going to touch base on some of those in this video, but as you'll see, A, B, and BC don't address them. So like infinity minus infinity is not addressed in the College Board AP, AB, and BC Calculus exam. So we're going to throw this into this video. It means it's going to go a little bit longer, but it definitely means that the focus of the video, the focus of the stuff that you're going to see essentially early on in the video is either 0 over 0 or infinity over infinity, and that's really what your AP is going to largely be on. So if you start to stress about the end of this video and some of the harder problems, don't be too stressed. That's not the focus of your AP. So here's L'Hopital's rule. If you have a limit as x approaches a of f of x over g of x, and that limit is either a 0 on top of a 0 or an infinity on top of an infinity, and I'm going to go ahead and throw in there that it could be a plus or minus in front of either of those, right? It doesn't matter if there's a negative in front of the 0 or a negative in front of the infinity. So it doesn't matter. Then essentially what you can do is apply L'Hopital's rule, which means that you can differentiate the top. So you can take f of x and make the top f prime of x, and you can differentiate the bottom and make it a g prime of x. And that those two limits should be equal. And you can keep applying L'Hopital's rule until you get a form that is not indeterminate, meaning like a numerical answer. So if after you apply L'Hopital's rule, you still get a 0 over 0, then you can use L'Hopital's again, and so on and so forth. So let's go ahead and walk through what this looks like. So we're going to start with one that frequently we tell people to memorize. The answer to this limit is a 1, and I often tell students to memorize it early on, and that I will tell them eventually that they'll know how to figure it out. So if I were to plug in, I would get sine of 0 on top of 0, which is definitely a 0 over 0. Remember that that is never the answer. We saw that earlier. When we were doing limits early on, and we were learning how to simplify them algebraically. So that's not the answer. But what that tells me is that I'm okay to do L'Hopital's. So I always say okay to lop, right? So I'm okay to do L'Hopital's. So L'Hopital's says that the limit as x approaches 0 of sine x over x is equal to the limit as x approaches 0 of the derivative of sine, which is cosine, over the derivative of x, which is 1. Again, this is not finding the derivative of sine x over x, which would require a quotient rule. This is L'Hopital's rule, which says you can differentiate the top and differentiate the bottom, and it has to be in a limit. So now when I plug in, I get cosine of 0 over 1. Well, that's a 1 over 1, which is totally just a 1. So the answer to this problem is that the limit as x approaches 0 of sine x over x is a 1. And that's it. That's my answer. All right, so moving on. You're going to go ahead and try this one. All right, so try P1. You can pause me if you want. You should always plug in to make sure that it's okay to do L'Hopital's. So this is going to be a 1 minus a cosine of 0 over a 0. Well, that's a 1 minus 1 over 0. It's definitely a 0 over 0. So that is not the answer, but it means that I'm okay to do L'Hopital's. So okay to lop. So when I do L'Hopital's, I'm going to get the limit as x approaches 0 of, now when I differentiate 1 minus cosine x, the derivative of 1 is 0. The derivative of a negative cosine x is going to be a negative of a negative sine x, right, on top of a 1. So if I clean that up, I'm not differentiating again. It's just really ugly, and so I'm going to make it look nicer. That's a sine x on top of a 1. So now when I plug in, I get sine of 0 over 1. Well, that's definitely a 0. And 0 is a determinate form, right? So it's not an indeterminate form, and that's my answer. All right, so let's do the limit as x approaches 0 of e to the 3x minus 1 all over 2x. So the first thing I do is I plug in, right? So that's going to be e to the 0 minus 1 over 2 times 0. That's definitely 1 minus 1 over 0, which is 0 over 0. So that's not the answer, but it tells me I'm okay to do L'Hopital's. So when I go to apply L'Hopital's, I'm going to get that this is the limit as x approaches 0 of the derivative of e to the 3x is e to the 3x times the 3 for the chain rule, minus a 0 because I differentiate the 1 and get a 0. And on the bottom, I get a 2 when I differentiate 2x. So now when I plug in, I get 3e to the 0 over 2, which is a 3 halves, and that's my answer. All right, moving on to P2. So go ahead and give it a try. Again, you should always plug in just to double check that you can use L'Hopital's, but sure enough, when I plug in, I get a 0 over 0, right? So I'm okay to do L'Hopital's. So once I know I'm okay to do L'Hopital's, now I differentiate and get that this is the limit as x approaches 0 of the derivative of 5x is a 5, right? When I differentiate the 1, I get a 0, and when I differentiate this negative e to the 2x, I get negative e to the 2x all times 2. So now when I go to plug in, I'm going to get a 5 over essentially a negative 1 times 2, right? Because e to the 0 would be 1, so I get a negative 5 halves. All right, moving on. So now we have our first infinity over infinity. So when I plug this thing in, so someone sitting here is going to say, hold on a second, Hogan, we've done this before. I remember from horizontal asymptotes that this is totally 3/4. And if your brain is saying, hey, wait a second, I don't have to use L'Hopital's, this answer is totally 3/4, you are correct, and that is dope and awesome. Knowing more stuff than someone else isn't cheating, it's just awesome. So if your brain was able to do this without L'Hopital's, totally cool. So you can logic this with your prior knowledge without L'Hopital's. And that's great, and it's not wrong, and it's totally awesome. But let's walk through what would happen if we plugged in. If we plugged in this stuff, on top I'm going to get a bunch of infinities, and on the bottom I'm going to get a bunch of infinity minus 6, which is definitely still infinity over infinity. What that tells me is I'm okay to do L'Hopital's, right? So when I differentiate, I'm going to get that this is the limit, as x approaches infinity, of a 6x plus 2 all over an 8x not minus anything. Well, when I plug in, I'm still going to get 6 infinity plus 2, which is definitely infinity, over 8 times infinity, which is definitely infinity. So I'm okay to do L'Hopital's again. If I differentiate again, right, so I differentiate again, and the top just becomes a 6, and the bottom just becomes an 8, well, look, there's my limit. It's a 3/4, which is totally what we got logically by using our prior knowledge, because prior knowledge is awesome. All right, next one. So here we're looking at the limit as x approaches negative infinity of this. Now, if some of you sitting here watching this right now are thinking, hold on a second, Hogan, the top degree is smaller than the bottom degree. This thing has a horizontal asymptote of 0. Hey, that's totally the answer. Yeah, that's cool. You're right. That's awesome, right? So you can do this without L'Hopital's if you know other information, which is fine. But if you were to plug in infinities, you would definitely get the top is a huge infinity minus 5, which is infinity, and the bottom is a huge infinity plus, so a huge negative infinity, right? And then smaller infinities, so this thing would net negative infinity because this is so much bigger than the 3x, but either way, that's still an indeterminate form, so I'm okay to do L'Hopital's, right? So I go ahead and apply L'Hopital's, and I get that this is the limit as x approaches negative infinity of 12x over a 3x squared plus 3. And when I plug in on the top, I definitely get a negative infinity. And when I plug in on the bottom, I definitely get a positive infinity. But that's still an indeterminate form, so I'm okay to do L'Hopital's. So when I differentiate again, I'm going to get that this thing is a 12 on top of a 6x, which is definitely a 12 on top of something that is infinitely large, and that is 0. We've seen that before, right? When you have something finite on top of something that is infinite, sorry, it's a negative infinity, but it doesn't really matter. It's going to 0. And hey, look, that's the same answer we got if we did it logically. All right, cool. So now we're going to go ahead and do another one. So when I look at this, right, when I plug into this, I'm going to get that the top is a negative infinity squared, right, and the bottom is an e to the infinity. Both of those are infinitely huge. They're both massive. So it's okay to do L'Hopital's, right? They are both infinite values. An infinity over another infinity, even if they're different sizes, is still infinitely large. So when I differentiate, right, I'm going to get that this is the limit as x approaches negative infinity of a 2x on top of a negative e to the negative x, right? The negative comes from doing the chain rule. So when I plug in, again, I'm going to get a massive infinity on top of another massive infinity, which is huge. So again, I'm okay to do L'Hopital's. But again, that indeterminate form is never the answer. So I'm going to get that this is the limit as x approaches negative infinity of a 2 on top of what will now become a positive e to the negative x because of that chain rule again. Well, that's a 0 because remember, if you have something finite and you have something that's going to be infinite, when you divide something finite by something infinite, you get 0. All right, so we get 0. Moving on. All right, so last one here, right? Same idea. When you plug in, you get a 3 times something infinitely large over an e to something infinitely large. That's definitely an infinity over infinity. I'm okay to do L'Hopital's. Now, so far, you might be thinking, geez, Hogan, why do you keep doing this thing where we check and see if we're okay? It's obvious all of these are L'Hopital's problems. But when we get to the next section, you're going to see ones that don't look this way. So I differentiate the top and get a 6x. I differentiate the bottom and get an e to the 2x times a 2. Right, now if you want to cancel a 6 and a 2, you totally can. It doesn't matter to me. If you plug in, you definitely still get something infinitely large over something infinitely large. So again, I'm okay to L'Hopital's. If you wanted to cancel the 6 and the 2 to make your number smaller, that's fine. I don't really think it's a huge benefit, so I'm just going to ignore it. So when I differentiate again, the top is now just a 6, and the bottom is going to become a 4e to the 2x, right? Because when I apply that chain rule, I'm multiplying by 2 again. Well, now I have a finite number over something that is infinitely large, and that means that this is a 0. Now, I'm going to be honest and tell you that if you do enough of these problems, you can actually intuit this answer, because when x is the exponent, it is always a much larger number than when x is the base. So for any large value of x, x to the n is much, much smaller than n raised to the x, right? So as the x values get big, it's always more significant if the x is the exponent. All right, so moving on. All right, so there's a bunch of indeterminate forms, right? L'Hopital's can only be applied to 0 over 0 or infinity over infinity. So when we have 0 over 0 or infinity over infinity, which are the examples we just saw, right? These are really straightforward. So we just did these in examples. So we did E1 to E4 and P1 to P4, where it was very straightforward. It was one of these kinds of problems with infinities or with zeros, right? But if you're given one of these other indeterminate forms, like something infinitely large minus something infinitely large, your brain might say that that's 0, but it's not 0. The reason it's not 0 is because that's not how infinities work. So let's take a quick minute, and I want to talk about why these are called indeterminate forms. So let's add a quick slide, despite the fact that I didn't originally intend to do it. The way you can spot an indeterminate form, is that it has conflicting math rules. So they have conflicting math rules. It usually involves, so there's usually, in fact always, usually a 0 or an infinity is involved. So let me show you what I mean by that. I'm going to pick the easiest one I can think of. If I ask you what some number to the 0 is, you're going to tell me that it's 1. But if I ask you what 0 to a power is, you're going to tell me it's 0. So then when I give you 0 to the 0, uh-oh. What is it? Is 0 to the 0 a 1 because 0 is the exponent, or is it a 0 because 0 is the base? Well, it's neither. It can't be both 0 and 1, right? It can't be both 1 and 0 because that's just definitely not how math works. In fact, all of computer science is built on the fact that 1s and 0s are different. So this is what we call an indeterminate form. Okay, so there's other examples of this, right? So if we think about some of the other ones that we just talked about, right? So let me show you another example of one, okay? So for instance, a number over itself is supposed to be 1, and 0 on top of any number is supposed to give you 0. Okay, well then what's 0 over 0? Is it 1 because it is a number on top of itself? Is it 0 because it's 0 on top of a value? Is it undefined because 0 on the bottom is undefined? In fact, we can add that one too. A number on top of a 0 is what we call undefined. So the question is, right, this setup could be one of those three things. Well, it's not any of those three things. It's called an indeterminate form. So indeterminate forms are generally forms that cause some sort of a math issue where if you're following all the math rules that work for every other set of numbers, they don't work here. The same logic could be applied for infinity over infinity, right? So a number over itself should be 1, right? We've seen that a number over something infinite should be 0, right? And we've also seen that infinity over a finite number should be infinitely large. Well, then the question becomes, what is infinity over infinity? Which of those three is it? Well, it's not any of them. It's what's called an indeterminate form, okay? So if we actually, I'm going to hop down here for a second and show you another one, right? So there are others, right? So another example is infinity minus infinity, right? Why is that weird? Well, if I give you a number minus itself, I should get 0, right? But if I add an infinity plus or minus anything, I should get something infinitely large. So is this number infinity? Is this number 0? Well, it's neither. It's called an indeterminate form. So that's the idea behind what we mean by these indeterminate forms. And if I go back a slide, you'll see there's a bunch of them, right? There's 0 to the 0, 1 to the infinity, 0, so 0 to the 0, 1 to the infinity, infinity to the 0, right? And these all, and 0 times infinity, right? All of them, if you look at those other options, they all fit in the categories that I just described to you where something's wrong mathematically, right? So let's look at those other ones real quick. Like if I give you 1 to the infinity, well, you know that 1 to a power is supposed to be 1. Right? But you also know that if you put a number to an infinitely large power, it should be infinity. So is this thing a 1 or is it an infinity? Well, it's neither. It's called an indeterminate form, right? Because it could, so that's the idea when I say that an indeterminate form is like a violation of math rules, right? So let's look at one of those other ones real quick. So let's look at 0 times infinity, right? Well, the trick is that 0 times a number should give me 0, right? But infinity times a number should definitely give me infinity. So if I multiply the two of them together, do I get 0? Do I get infinity? I don't get either. I get an indeterminate form. And these indeterminate forms behave weirdly. That's why there's a whole set of like different rules for them sometimes. And there's this thing called L'Hopital's, right? I think the last one that we didn't do was infinity to the 0, and that's similar to 0 to the 0, right? Because if you have a number to the 0 power, it should be 1, but if you have infinity to any power, it should be infinitely large. So the question is this a 1 or an infinity? Well, it's neither. It's an indeterminate form, okay? So again, that was just like a little bit of a sidetrack that I didn't originally have in the slides, but I just wanted to touch base by what we mean about that. So if you have any of these other indeterminate forms, and I think I covered all of them, you're going to have to do some kind of simplifying first and then L'Hopital's. So what I will say is that this one might be on the AP. Because as you'll see in a second, it's the easiest of these options of weird-looking things. These 4 are pretty tricky, and so we're going to look at them, but I will say that of them, I think the one that is most likely to be on the AP if they're trying to give you a hard question is the 0 times infinity, and we're going to go ahead and look at that. Okay, so this is actually a perfect example of that. Let's look at what this is. If I were to plug in, I would get an e to the negative infinity times the square root of infinity. Well, e to the negative infinity is the same as this, right? So this is a 0 times an infinity, because square root of infinity is still infinitely large, and 1 over something infinite is 0. So this is definitely an indeterminate form. So this is indeterminate, but the issue is that it's not 0 over 0 or infinity over infinity, and L'Hopital's requires a fraction. So what I have to do here is I need to rewrite this indeterminate form so that it looks like one of these two. So what I'm going to do is recognize that I could put this guy on the bottom of the fraction, right? I could flip him so that now this looks like this, and suddenly, now when I plug in, I get an infinity over an infinity, and I'm okay to do L'Hopital's. So the trick is that this product one is pretty likely to show up, because although it's technically not one of the original, sorry, one more back, it's not one of these original two that the AP specifically specifies, this is a really easy version of simplifying to get to that spot. So I think it's possible you'll see it. So now when I do L'Hopital's, right, I'm going to get that this is the limit as x approaches infinity of, so the derivative of x to the 1/2 is a 1/2 x to the negative 1/2, right? But usually we just skip to the end and realize that this is what a 1/2 x to the negative 1/2 looks like, and the derivative of e to the x is e to the x. Well, if I clean this up a little bit, I'm going to get that this is the limit as x approaches infinity of, essentially all of these are going to end up on the bottom, right? So this, and again, this is just simplifying, this is not L'Hopital's, right? This is the limit as x approaches infinity of a 1 over 2 root x e to the x, which means this is definitely going to a 0 because a 1 is definitely a finite number, and these are definitely going to infinities. Now, again, I kind of mentioned before that I can spot that because I've done a lot of these problems. Right here, I noticed that the e to the x is going to be way bigger than a square root of x, like so much bigger that it is going to be infinitely larger than the square root of x, so I can look at this and know that it's going to 0. I'm not suggesting that necessarily you do that. I'm only saying that I've done a lot of these problems for a very long time. All right, so go ahead and give P5 a try. It's the same idea. First thing you'll notice is that when you plug in, you're going to end up getting a 0 times an infinity, right? Because you're going to get a 1 over e to an infinity, and you're going to get this infinity squared, which is definitely fitting in this category. So it is indeterminate, but you need to rewrite it so that it's a fraction, right? So you need to rewrite this. So when we rewrite this, the easiest way to rewrite it is to put the guy with the negative exponent on the bottom. So I'm going to get that this is the limit as x approaches infinity of an x squared over an e to the x over 2. When I plug in, I definitely get infinity over infinity, which means that I'm okay to do L'Hopital's, right? So I get that this is the limit as x approaches infinity of a 2x over a 1/2 e to the x squared, right? Because it'd be e to the stuff times the derivative of the stuff, right? When I plug in, I still get an infinitely large thing over an infinitely large thing, but I'm okay to do L'Hopital's, right? And again, if you start to see these problems more often, you're going to get to the point where you can look at this and say, oh, hey, I know where this is heading. This is going to be a 0. Because what's going to happen is the bottom is always going to have an e to the stuff. And the top is now a finite number, but the bottom is still going to be infinitely large. So this is going to end up being 0. And again, as you get better, you can kind of look at it here and say, wait a second, this x squared is way smaller than e to the stuff. This is definitely going to go to 0. All right, cool. So now we're going to go ahead and do one of the ones that's a little bit different. So if we plug in this infinity, I get 1 plus 0 raised to the infinity, which is a 1 to the infinity. This is an indeterminate form, but I need to rewrite it. So this is a trickier problem, and I think this is harder than you'll likely see on the AP, but we're going to walk through how to do it. In order to do this problem, I need to say that the answer to this problem is L. Okay, so it's important to note that I'm going to call my answer is L, and we're going to deal with that later. The only way to get a power up top to drop down in front is to take the natural log of both sides of something. So if I take the natural log of both sides of this thing, and the natural log of L, because it has to be on both sides, I'm allowed to put the natural log inside the limit, right? The limit can be the limit of the natural log of the stuff, which is going to allow me to take this power right here and drop it down in front. Now, that doesn't make life a ton better, and the reason it doesn't make life a ton better is that multiplication is not what we want for L'Hopital's, right? What we want for L'Hopital's is division. So what I'm going to have to do to make this division is I'm going to have to rewrite this as division by 1 over x, because if you divide by 1 over x, it's the same as timesing by x. So this is the limit as x approaches infinity of this natural log over a 1 over x. And again, on the other side, I still just have this natural log of L. So now let's plug in and check. If I plug in and check, so let me just, I'll make a note right quick over here. If I were to check, right, so if I check for L'Hopital's, when I plug that infinity in, I get natural log of 1 plus 0 over a 0, which is definitely 0 over 0. So I am okay to do L'Hopital's. So what I'm going to get is that this is the limit as x approaches infinity. I'm going to differentiate this. So this is a 1 plus x to the negative 1, and this guy right here is also an x to the negative 1 if you're trying to differentiate. So I'm going to get 1 over the stuff times the derivative of the stuff, which is going to be a negative 1x to the negative second. On the bottom, the derivative of the stuff is conveniently going to be that exact same negative 1x to the negative second. And remember that that whole thing is still equal to the natural log of L. That's going to matter at the end. These two conveniently cancel, and I now get that this is the limit as x approaches infinity of a 1 over 1 plus 1 over x, and that's equal to the natural log of L. Well, now when I plug in, I get that this is a 1 over 1 plus 0 is equal to the natural log of L, which means 1 is the natural log of L, and when I exponentiate to solve, my answer is that L is E, Euler's number, right? So, interesting side note, if we go back up here for a sec, this is the definition of the number E. So this is the definition of E, the number that you use that is Euler's number. So when we talk about the base of the natural logarithm or the natural base E, this is the definition of that natural base E. Interesting side note. Okay, let's go ahead and do a similar one for P6. Okay, so P6, you're also going to have to use logarithmic properties, right? You're going to have to take a natural log. So I'm going to call the answer L, and I'm going to do a lot of math, right? You could plug in real quick. If you plugged in to check, what you're going to find really quickly is that the inside is a 1, right? Because essentially the inside's a 1 because look at those degrees, right? They both have the same degree and the coefficients are 2. So that inside's going to approach a 1 as x approaches infinity, and the top is an infinity. So this is definitely a 1 to the infinity, which is indeterminate but needs to be rewritten, right? And again, I don't know how much of these you would see on the AP, as you saw that exclusionary statement at the beginning of the video, but hey, it doesn't hurt to see how to do it. And if you're really not into this, if you're like, okay, cool, I don't care, then that's your choice. All right, so I'm going to take the natural log of both sides, and I'm actually just going to skip to the step where I put the natural log on the inside to save myself a step because this has been a long video. So this is going to drop down in front, right? But I'm going to warn you now that you want division, so you're going to end up doing the same trick I did last time, where instead of making this, so this is a root x, but you're going to make it division by 1 over root x, right? Because you want division, right? So you're going to rewrite this as the limit as x approaches infinity of this natural log, 2x plus 1 over this 2x minus 1, all over a 1 over root x. And that's going to equal your natural log of L. So now let's check if we plug in, if we're allowed to do L'Hopital's. So when we check this, right, when we check plugging in infinities, I'm going to get the natural log of 2 over 2, which is 1, over a 0, because that's a 1 over infinity. So sure enough, that's 0 over 0. I'm okay to do L'Hopital's. Now, it's not saying you're going to love the L'Hopital's, but let's do it. So when I do L'Hopital's, there's actually an interesting way you can deal with this logarithm, and I haven't talked about it yet, but you don't have to leave it as a quotient. So just, this is actually like a little side note. When you differentiate this log, you could also split it up into 2 logarithms. If you like this better, you could use log properties to differentiate each of these, and this is going to be easier to differentiate than if you leave it together. If you leave it together, you're going to have to use the quotient rule inside the natural log. Like you're going to have to, it's going to get a little messy. There's nothing wrong with it, but this is way easier to differentiate. If you do it this way, this is going to be your outer function, and when you do the inner function, it's going to be a quotient, and that's going to be a fairly long, messy problem. So you can do it either way, but I'm going to advocate that you rewrite this with algebra first and then differentiate. So now, when I apply L'Hopital's, right? So that's algebra, not calculus. I'm going to go ahead and differentiate and get the limit as x approaches infinity. When I differentiate it written like this, it's 1 over the stuff times the derivative of the stuff, which is going to be a 2, minus 1 over the stuff times the derivative of the stuff, which would be a 2. On the bottom, right, this was an x to the negative 1/2. So it's going to end up being a negative 1/2 x to the negative 3/2, which is crazy looking. I get it. It's no fun. But we can clean this up a little bit. So when I go to clean this up, and again, no promises that this is super fun and awesome, because this is a pretty ugly problem, right? But when I go to deal with this, right, so I'm going to get a common denominator here, right? Because if I plug in right now, it's essentially going to be a 0 minus a 0 on top and a 0 on the bottom, which is not helpful. But there's a chance that if I clean this up and get a common denominator by multiplying this thing by 2x minus 1 and this thing by 2x plus 1, and then I flip some stuff and clean it in a second, there's a chance that this turns out nicer. So I'm going to get that this is a 4x minus 2 minus a 4x minus 2 on top of this ugly monstrosity. And then essentially what's happening is I can flip, so this stuff, right? So essentially, this stuff can be flipped up to the top. It's up to you how you want to write this, right? This is actually a negative 1 over a 2x to the 3/2. So you could flip this and make this multiplication. So looks to me like I get the limit as x approaches infinity of the 4x and the 4x are gone. This just comes out to be a negative 4. So I seem to get an 8x to the 3/2 on the top, right? And on the bottom, when I FOIL this out, I get a 4x squared minus 1. So now, as disgusting as this thing started out, this is actually way friendlier. If I plug in, I still get infinity over infinity, but I'm okay to L'Hopital's, and this is going to go a lot better. Now, I could do L'Hopital's, or I could recognize that 2 is a bigger power than 3/2. So once I know that, this thing is going to 0, right? I can either do this with logic, because I know that the power of the polynomial on the top is smaller, or I can do L'Hopital's. If I choose to do L'Hopital's, I would get the limit as x approaches infinity of, when I drop the 3/2 down, I'm going to get 12x to the 1/2, right, over an 8x, right? And again, you can see the top is smaller. If you do still see that it's infinity over infinity and you're not seeing that it's 0, it's okay to do L'Hopital's again, right? If I do L'Hopital's again, I'm going to get that this is the limit as x approaches infinity of a 6x to the negative 1/2 over an 8, which when I rewrite that is going to end up being the limit as x approaches infinity of a 6 over 8x to the 1/2, which is definitely a finite number over an infinite number, which is totally 0, which is what we got a couple steps back. So again, really long problem, but that's not my final answer, because after all of that, remember that the very first thing we did was set all of this equal to the natural log of L. So this is equal to the natural log of L, which means that my answer, the natural log of L equals 0, when I exponentiate, I get that L is a 1. So after all that work, so this is a really rough problem, right? It's a rough problem. And again, I don't think that realistically, if we go back up to that exclusionary statement, or if we think about what that said at the very start of this video, right? Realistically, you're largely going to be seeing 0 over 0 or infinity over infinity, so don't panic if these seem really hard. You should be able to do those 0 over 0 and infinity over infinities. All right, so let's go ahead and plug this one in, right? If I plug this one in, I get 0 raised to the 0. The hint that we're going to have to do a logarithm is definitely that exponent again, right? So I'm going to call my answer L, right? I know that L is my answer, and I'm going to go ahead and take the natural log of both sides. One of the nice things about this is that once you see this trick, it's the same trick every single time there is an exponent on x stuff, right? And on the other side, I get the natural log of L. Right? I drop the x down, and again, once you see that trick that I don't want to leave it as an x natural log of sine x, I want to rewrite it as dividing by 1 over x. Once you see that trick, it's the same trick every time. So, so it's this same trick where I'm going to rewrite this as division of 1 by 1 over x, and that's my natural log of L. So now, when I check and see if I can apply L'Hopital's, right, when you look at 1 over x and you apply infinity, or you apply 0 from the positive, if you picture the graph of 1 over x, this is why they give you the 0 from the positive here instead of 0 in both directions. This is what the graph of 1 over x looks like. And you might be thinking, how would I know that? Well, because you want to memorize basic graphs. So this is going to a positive infinity. So this thing down here is definitely an infinity. And on the top, the natural log of sine of x, when you plug in 0, that's the natural log of 0. Well, you have to figure out what a 0 graph, or what a log graph is looking like. That looks like this. That's definitely a negative infinity. And again, that's why they're having you approach from the right, because there is no log graph on this side, right? So it matters that there's a direction. So point being, I get negative infinity over infinity, which means I'm okay to do L'Hopital's, right? So now I go ahead and do my L'Hopital's. Remember that this is actually an x to the negative first when I differentiate. So I get that this is the limit as x approaches 0 from the positive of 1 over the stuff times the derivative of the stuff on top of a negative 1 x to the negative second, right? So now, right, what's going to happen, and that's my natural log of L, right? So I get that this is the limit as x approaches 0 of, so this is going to end up being a cosine over a sine, right? And then this is divided by a negative 1 over x squared, so we should flip and clean this up a little bit. So this is going to be the limit as x approaches 0 of a cotangent theta, sorry, not theta, x, come on brain. And then that x is going to flip up, right? So I'm going to get negative x, well, that's not helpful. I want to keep it as division, don't I? So we're going to make this cosine x sine x. You don't want it to stop being division because if you want to apply L'Hopital's, it's got to be division, right? So this is going to be, I ran out of space for my limit. The limit as x approaches 0 from the positive, sorry, I dropped the positive here by accident, of this negative x squared cosine of x all over a sine of x. If I plug in again, right, if I plug in to check, when I plug in, I definitely get a 0 on top of a 0, so I'm okay to L'Hopital's again. But again, this is a pretty hard problem. So when I L'Hopital's again, this is going to be a product rule. So I'm going to get that this is the limit as x approaches 0 from the right of u dv plus v du, right? And on the bottom, I'm going to differentiate and just get cosine. So this is the part that's important because all of a sudden things are going to work out a little bit better. Now when I plug in, the bottom's just a 1. So when I plug in, I'm going to get 0 plus 0 over 1, which is 0, and my answer is 0. But recall that this was one of those situations where 0 was equal to natural log of L. So my L is going to be e to the 0, which is 1. And that's my final answer. So again, not a short problem, but that's okay, right? These are harder than what you'll likely see on an AP. Okay. So last one is going to be an infinity minus an infinity, because essentially this is a 1 over 0 minus a 1 over 0, which is an infinity. So this is infinity minus infinity. So this is definitely more difficult than you're going to see on an AP, AB, or BC, but we're going to go ahead and walk through this. So the issue first is that I should try getting a common denominator, right? So what I'm going to do is I'm going to multiply the second fraction. So I'm going to use some algebra, right? We're going to lean pretty heavily on our algebra here. I'm going to get that this is the limit as x approaches 1 from the right of, I'm going to multiply the first fraction by x minus 1 over x minus 1. So I'm going to get an x minus 1. I'm going to multiply the second fraction by the natural log, and the bottom common denominator is going to be this product, right? These two things multiplied together. Okay, so now if we were to plug in, right, I still get a 0 on top of a bunch of zeros. So so I get a bunch of zeros, but now when I plug in, I get 1 minus 0 over 0 times 1 minus 1, which is definitely a bunch of 0 over 0, so I'm okay to L'Hopital's. So that was the big trick there, is that I need to get a common denominator to combine them. Excuse me. Now that I'm okay to do L'Hopital's, I will have a product rule when I do the bottom. The top is pretty straightforward. So this is going to be the limit as x approaches 1 from the right of the derivative of 1, x is 1, the derivative of the 1 is 0, and the derivative of natural log of x is 1 over x. On the bottom, I'm going to have u dv plus v du, right? And so then we're going to have to clean this up and see what happens, right? So when I clean this up, right, and I could actually plug in, I could plug in now, but I'm going to wait and see if we can clean this up a little bit first, just because we're going to have to differentiate it, and it'll be a lot easier if we clean this up. So this is the limit as x approaches 1 from the right of a 1 minus 1 over x, right? And on the bottom, I get natural log of x. When I distribute this 1 over x, I'm going to get plus 1 minus a 1 over x, right? So when I plug in, right, if I plug in again, I'm going to get 1 minus 1, which is definitely a 0 on the top, and on the bottom, I'm going to get 0 plus 1 minus 1, which is definitely a 0. So yet again, it's a 0 over 0, and I am yet again okay to do L'Hopital's. So I get that this is the limit as x approaches 1 from the right. So when I differentiate the 1, it's just gone, right? And when I differentiate this thing, this is actually a negative x to the negative first, so I'm going to end up with a positive x to the negative second, which is the same as a 1 over x squared, right? When I differentiate the natural log, I'm going to get a 1 over x. The 1 disappears. And when I differentiate this thing, I'm going to get exactly the same thing that I got up top when I differentiated it, right? So now if we plug in, When I plug in, I get 1 over 1, and on the bottom I get 1 over 1 plus 1 over 1, so I get 1 over 2, and that's my answer. I didn't have to take a natural log at any point, so I don't have to worry about exponentiating when I'm done. And after all that, that is our crazy L'Hopital's video, and that is the end of Unit 4.